Hi, and welcome to this lesson on garbage collection. Now, in the previous video, we took a look at something called reference counting. So remember what reference counting is. As we create objects in memory, Python keeps track of the number of references we have to those objects. There could be one reference, two references, three references, but no matter what the number of references is, as soon as that reference count hits 0, the Python Memory Manager then reclaims, it destroys that object and reclaims the memory. So that's called reference counting. But sometimes that just doesn't work. And in particular, we have to look at a situation called circular references. So what are circular references? Well, let's take a look at an example. Let's say we have a variable, myVar, and let's say that myVar points to object A. So far, it's exactly what we've seen. If myVar goes away, if we point it to another object or to none, then the reference count of object A goes from 1 to 0, and the Python Memory Manager at that point destroys the object. So far so good. But let's suppose that object A has an instance variable, let's say var1, that points to another object, let's say object B. So at this point, what happens if we get rid of that myVar pointer? Let's say we point it to none. Then the reference count of object A goes down to 0. Now the reference count of object B is still 1 because object A is pointing to B. But the reference count of object A has gone down to 0, and so by reference counting, it will get destroyed. Once it gets destroyed, object B's reference count also goes down to 0, and it gets destroyed as well. So by destroying myVar, by removing that reference, the Python Memory Manager, through reference counting, will get rid of object A and B. So far, no problem. But now, let's suppose that object B also has an instance variable, let's say var2, and var2 points back to object A. Now we have a circular reference. So what happens if we get rid of the myVar reference? So if that goes away, then the reference count for object A, you will notice, is 1 still, right? It was 2 because myVar was pointing to A, B was pointing to A, so A had a reference count of 2. myVar went away, right? So the reference count now on A is 1. It's not 0. And the reference count on B is also 1 because A is pointing to B. So in this case, reference counting isn't going to destroy either A or B. It can't because they both have references. They both have a reference count that is non-zero. And that is called a circular reference. And because the Python Memory Manager cannot clean that up, if we were to leave things as is, we would have a memory leak, right? Because myVar went away, but object A and B didn't. And there's no way that they'll get destroyed. Not through reference counting. So that's where the garbage collector comes in. The garbage collector will look and will be able to identify these circular references and clean them up. And so the memory leak goes away. We do get cleanup. So the garbage collector can be controlled programmatically using the GC module. There's a built-in module to Python called GC for garbage collector, where you can interact with the garbage collector and you can even modify its behavior. So by default, garbage collection is turned on. Now you can turn it off. So you can turn it off, but you really have to be absolutely sure that your code is not creating circular references, because if it does, you will end up with memory leaks. And it's very easy to create circular references and, without even knowing that you've created that circular reference. So be very, very careful if you do turn it off. Now, why would you want to turn it off? Well, it's really just performance reasons. The garbage collector is something that runs periodically, by default about every minute or so, and it has to identify these circular references, so obviously it takes a little bit of computing power to do so. And so you may want to turn it off. But this is really more advanced and you have to be careful. I would just leave the garbage collector turned on unless you have a specific need to turn it off. So it runs on its own. If it's turned on, you can turn it off. You can also call it manually, and you can also interact with the garbage collector to see what's in there that needs to be cleaned up, especially if you've turned it off, and do your own cleanup. And so some people do that. There's other ways you can also avoid having to do your own cleanup. You can use weak references. There's a variety of things that you can do. We'll look at weak references when we get to the sections on object-oriented programming. But for now, just be aware the garbage collector is there to really clean up circular references. It's turned on by default, and you really should leave it on. So in general, it works just fine. But as always, there's a caveat. It doesn't always work. But this really applies to Python versions of less than 3.4. So as long as you're using Python 3.4 and above, 3.6 as of this recording, then you're fine. What was happening before is that if even one of the objects in the circular references had a destructor, so for example, if you're creating your own class, you can create a constructor for the class, yes, but you can also create a destructor. Now the destructor is code that you run when you're destroying the object. And typically you might put things in there that might be cleaning up files, maybe deleting files that you created that were needed during the duration of that object, maybe closing a database connection, whatever it is. And you would put that code in this delete method, in this dunder method. So if even one of the objects in the circular reference has a destructor, then the order of the destructors might be important, right? The order in which you destroy your object might be important. Maybe you cannot close the database connection until some other class that you have that was dependent or that was in the circular reference maybe deletes or commits a transaction or rolls back a transaction. Who knows, right? There could be steps or a certain order in which those steps have to be taken. So the garbage collector doesn't know what that order should be, and it would basically mark those objects as uncollectible. It would say, you know what? I don't know how to handle this. I'm not going to do it. And so when you had that situation with a circular reference where at least one of the objects had a destructor, then they weren't getting cleaned up, not by the garbage collector, and of course not by reference counting, and we would end up with a memory leak. Now that is no longer the case with version 3.4 and up. That particular problem has been resolved. So I really suggest that you do not use Python less than 3.4. Right? Use Python 3.4 and above. All right, so let's take a look at some code and just put the garbage collector module through its paces and see what happens with circular references. So the first thing we're going to do is we're going to import the ctypes library. Recall from the last video we're going to use that to look at the reference count given a memory address. We're also going to need to import GC, which is the garbage collection module. Okay, and we're going to bring back that same method that we had before to find the reference count for an object at a given memory address. And just return ctypes.clong.from address.value. Okay, so just what we had before. Nothing new here. Now, what is new is we're going to look at a method that's going to dig into the garbage collector, and it will tell us whether that object exists in the garbage collector or not. And we'll do that again by memory address. So we're going to define a new method. Let's call it object by ID. And we'll pass in the object ID or the memory address. And we're going to loop through every object in the garbage collector, and we're going to call the object getObjects method of the GC. That will basically look at every object that's inside the garbage collector. There's a lot of objects that get generated, and that's going to be the easiest way for us to find the object we're interested in. And we'll say if ID of object equals the ID that we passed in, right? So we're just going to compare memory addresses. We're going to say return object exists, right? And if we exhaust the loop, then we'll return not found. Okay. So this method is basically going to look at all the objects that are tracked by the garbage collector, and it will try and find the object that we're interested in by comparing the IDs. Okay. Now, there's another way that we can compare memory addresses, and we'll get to that in some future lesson. All right, so now comes time to create those two classes that are going to create a circular reference. So let's go ahead and create class A. Now, if you don't know object-oriented programming in Python, don't worry about it. These are pretty straightforward. And as I said, we'll dig into object-oriented programming in a lot more detail in a future section. So we're going to create a constructor, and that constructor is basically going to call another class that we haven't created yet. And what it's going to do, it's going to set its B variable equal to an instance of the class B passing self. Now, self in this context means A, right? Means this instance of A. So we're going to pass the instance of A to B. And in B's constructor, we'll store that reference. So right now we're setting up that circular reference in exactly the same way we had in that diagram just a little while ago. So we have that, and then we're going to print some stuff out. Let's go ahead and print A. We'll print out what self is, and then we'll print out what B is. And by print it out, we're going to print out the memory address. So dot format. So what are we going to print out for A self? So we're in the A instance. The self, which is going to be the instance of A, is going to be hex of ID of self, right? And for B, we're going to print hex of ID of self.b. Okay? So basically, when the class instantiates itself, we're going to print out the memory addresses of the references. We're going to print out the memory address of ourself, the instance of A, and we're also going to print out the memory address of the B instance that we created in this line here in the constructor. Okay, so that's class A. Now we need to do class B. And class B, again, we're going to declare an initializer. And here, we're going to say self. Now the initializer takes in an extra parameter. Let's call it A, right? That is what's being passed when B calls, gets called, gets constructed. We pass in this reference to A. So that's going to come in here. So be careful. The self here and the self there don't mean the same thing. Self refers to the instance of this class B. Self here refers, and this self refers to the instance of class A in the code. So here we're going to set self.a equals A, right? So we're going to store the reference to A. And we're going to print out something very similar. So I'm going to copy paste. But now, of course, we're in class B, and we are going to print out ourselves. But now we're not going to print out B, we're going to print out A. That's the internal variable A. And so we're going to return the memory address of A. Okay? So now we've set up those two classes, A and B, with a circular reference. The next step, we are going to disable the garbage collector so we can see what's going on. Because If we don't disable it, then as references go away, it's going to clean up the circular reference, but I don't want to clean it up now because we really want to take a look at what's going on. So we're going to disable the garbage collector. And now let's go ahead and create myVar. Now myVar is just an instance of A. And the initializer for A doesn't take any variable, any parameter. Okay, so as you can see, both the constructor for B ran, this is what it printed out. Okay, it said its reference was this number here, and then the reference for A was that 182F16 whatever. And you can see the constructor for A ran also. Now you can see that the memory address of A here is the same as the memory address of A here, right? This one is the A object self, right? And this is the B's .A memory address, right? This is the circular reference. And then these two are also equal to each other. Again, this is the reference that A holds to B, right? This is the memory address of the instance of B, and it's the same memory address here. Now, in fact, we can look at the ID of myVar. Now, what do you think that should be? I'll let you think about it for a few seconds. myVar is pointing to A. So the memory reference of myVar should be exactly what A is, which is this one right here. Okay, so that matches, so that's good, right? So far, so good. Okay, so now, I mean, there's another way you can look at it as well, right? We can look at print, let's say myVar.b, and myVar, remember, B is an instance property of the class A. So myVar, which is an instance of A, has this property B, and we can call hex of ID of myVar B. We can also print, now we're going to print myVar.b. Now myVar.b is an instance of class B, and it has a property called A. So we can say .a. And again, we're going to print the memory address of that as well. So if we print that, you'll notice that B, this should be the memory address for B, right? Which is exactly this one here. And this is the memory address from A, which is this one right here. And you can see that we recovered the memory address from A by looking at the object instance of B. Okay, so we have that circular reference. All right, so now let's take a look at a few things. Let's go ahead and print. Let's print the reference count. So I'm just going to print it like this, ref count. Remember that method that we created, right? Actually, before I do that, I need to hold references to A and B. So A.id equals ID of A, and B ID is equal to the ID of B. I don't need to store the ID of myVar because it happens to be the same as the ID of A, since they're both pointing to the same object. And what did I do here? Oh, ID of A is myVar. Sorry, right? We don't have a variable A. And the ID of B is simply myVar.b. Okay, that's a little bit better. And again, we can check that just to be absolutely sure. Okay, we should probably, I'm storing the decimal because that's what we need to pass to those two functions, but I'll print out the hex version. Okay, as you can see again, A is this reference here, and B, well, myVar.b is this reference dot here. Okay, and you'll see why I'm storing those memory addresses. We're going to need to have the stored memory addresses once those objects go away. We won't be able to access them by using myVar because we're going to get rid of myVar, right? So we're going to need to store those addresses. All right, so let's take a look at the, we're going to call our method ref count of AID. Now what should that be? Well, there should really be 2, right? Because my var is pointing to A and B is pointing to A. And that's indeed what we get. Now, what about the ref count for the B object? Well, the ref count is 1, right? Because only A is pointing to B. So that all seems to work out. Now, we're also going to use that new method that we defined. Remember this one up here, object by ID. We're going to look in the garbage collector to see, is that object there? So we're going to say object by ID, and we're going to pass in the ID of A. And the object exists, right? Yeah, okay, cool. That's what we expected. And let's do the same thing for B. And the object exists. All right, good. So we have those references. We see what the reference count is, okay? So now let's go ahead and set my var equal to none. So basically, I'm destroying that reference between my var and A object, okay? So now let's look at the reference count of A. And the reference count is 1. And then the reference count of B is also 1. So as you can see, we got rid of my var, but there's still pointers to A and B because that's a circular reference. A is pointing to B and B is pointing back to A. And reference counting, therefore, is not going to help us out here because the reference count is non-zero. That's where the garbage collector comes in. Now, we can check still, make sure that those objects are indeed still being tracked by the garbage collector. You can see the object still exists. And we'll do the same thing with B. And we can see the object still exists. So those objects definitely are around. They have a reference count and the garbage collector is tracking them. But it hasn't cleaned them up. Why? Because we stopped the garbage collector, remember? Okay, so not something that you necessarily want to do. So now we're going to run the garbage collector manually. And we're going to say gc.collect. And that's how you can run the garbage collector manually. So now we've ran the garbage collector. And we're going to look at the object by ID of A underscore ID. It's not found, it's gone, right? And let's take a look at object by ID of B underscore ID. And it's not found. It's no longer in memory. So let's take a look at the reference count of A underscore ID. Oops. What's the method called? Ref underscore count. One. Now that's kind of weird, right? We should have destroyed that object. What about the reference count for B? That's weird. Let's try that again. Whoa. 1, 2, 5, 4. Now we have that many references to that memory address, but it should be 0. Well, what about A? Well, that's changed. Now it's some other big number. Now the odds are that when you run this code yourself, you'll get different numbers and you'll see them fluctuating, possibly. So what's going on? You want to think about that a little bit? What is going on? Why? We're not seeing the objects, right? If we try object by ID in the garbage collector, it tells us it's not in there. But I'm getting a reference count for that object, A.ID. And it seems to change over time. If we do it again, who knows what we're going to get? Well, we get the same number. But it's definitely not 0. Well, this is why we usually don't use memory addresses and we don't work with memory addresses in Python. unless you're trying to debug stuff or you're trying to do your own memory cleanup, you've got to be really careful using memory addresses. What is at that memory address right now? Remember the memory address that we stored for A, right? It was up here somewhere. Okay, a.id, right, was this value here, right? We stored it in a.id. What's in there right now? Yeah, we don't know. It could be something else. It could be nothing. Who knows? But that object is no longer A, right? It's no longer what this variable here was. It's no longer this instance of A. It's something else. And so trying to get the reference count of a memory address that is no longer necessarily managed by Python even, or even if it is, it's been reclaimed. Remember, the space, the memory address that was used by that variable was reclaimed. It's now being used for something else. Yeah, pretty obviously, right? And so who knows what that means? So you got to be very careful using memory addresses. It's okay to do this in this context. It's okay when you're trying to debug stuff. And it's okay if you understand what you're doing. And as long as you're using a memory address for an object that you know exists and you know what it is. But once the garbage collector ran, it destroyed all the objects involved in that circular reference. And those memory addresses we had stored are no longer applicable. Okay, so you really have to be careful with that. All right, thanks for watching, and I'll see you in the next video.